Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be talking about 4.1, which is getting into graphing rational functions. From Unit 4 to Unit 7, we're going to be looking at different types of functions. Rational is going to be the focus of Unit 4, then we get into looking at how to graph different types of functions, a little bit of review with exponential functions and application, and then once we do that, we're going to get to trigonometry, intro to pre-calc. But for the good remainder of the semester and most of quarter 3, we're looking at doing a lot of functions. Some of this is going to be graphing, some of this is going to be how we can shift and transform these functions. So hopefully it's not too bad, but we'll go ahead and get started here in just a second. Sorry. Where did that go? There we go. Wasn't loading for a second. Most of today I'm going to be using Desmos as we look in these functions. Desmos is our standard graphing utility. If you have a graphing calculator, you're welcome to use that as well. So what is a rational function? We've seen the parent rational function in Math 1 and Math 2 when we talk about them. This is your parent rational function, y equals 1 over x. So a couple of things we want to note here with a rational function. The first is that if I look here, I have what are known as asymptotes. An asymptote, if you recall, is a line that the graph approaches but never crosses. Specifically with rational functions, we have two. We have a vertical asymptote going up and down, and we have a horizontal asymptote going left and right. A couple of things on that. One, remember that an asymptote is a line that doesn't cross. So if I were to, say, zoom in on Desmos here, even if I go really, really small as I follow this graph up, right, it'll never cross that line. And vice versa, if I was looking at the horizontal asymptote, which also exists here, if I'm going left to right, it does not cross that line. So by default, my asymptotes for the parent function are y equals 0 and x equals 0. Okay. That will change based on where we shift the parent function to. We talked about this with quadratics in Math 2 very heavily, and a little bit towards the end there with other types of functions like cubic functions and so on and so forth. The process is going to be the same. You guys had a Unit 0.6 assignment that was review on Monday that kind of talked about exactly this. If you didn't get a chance to do it yet, I suggest that you go through. It's pretty straightforward, should be simple. So let's get our parent rational function back up here, and let's take a look at it. So when I change any type of function, going back to looking at quadratics, when I change any type of function, if I have a change that is outside where the variable expression is, that moves the graph up and down. So if you'll recall from Math 2 when we looked at quadratics, that's what I'm talking about. Plus 1, plus 2, plus 3, right? It moves the graph up. And similarly, if I do minus 1, minus 2, minus 3, it moves the graph down. That is true for any function. So looking at the rational function, if I add 1 on the outside, then it moves the whole graph up 1. And if I add 2, it moves the whole graph up 2. And if I add 3, it moves the graph up 3. And vice versa, if I subtract, minus 1 moves it down 1, minus 2 moves it down 2, so on and so forth. So not only is it shifting the function, and while we're speaking of functions, the name of this is a hyperbola. So Hyperbola, hyperbola. So any change outside moves the function up and down. If you think about it, you're really changing the output of the function. Adding 1 changes the output to be higher than 1, which is what causes it to move up. And if I subtract 1, I'm decreasing the output by 1, which is what causes it to move down 1. So even though I'm typically writing my changes over here on the right, it would be the same as if I was changing the y value, right? So if I put y equals 1 over x plus 1, and I write it like such, I get the same thing, right? I am changing the output, and it causes the function to move up and down. Okay. So that's the first part. And if you recall from our, again, quadratic days in Math 2, right? If I look at y equals, put it in vertex form here, a times x minus h quantity squared plus k, the k is what moved it up and down. The h, what moved it left and right. So if you change the input, then it moves your graph left and right. Now here for rational functions, our variable is going to be in the denominator. So if I say add 1, notice how it shifts left 1. That was the same with quadratics in Math 2. If I had a positive in the parentheses, it was moving it to the left. So y equals 1 over x plus 1 is moving it to the left 1 space, left 2 spaces, left 3 spaces, so on and so forth. And if I subtract in the denominator, or subtract from the input, that moves it to the right. So minus 1 in the denominator moves it to the right. Minus 2 moves it right 2. Minus 3 moves it right 3, so on and so forth. Just like with our unit and quadratics in Math 2, what I want you guys to be able to do is, if I give you a function, to be able to sketch it, and if I give you the sketch of a function, to be telling me the equation. So some of the questions will be just like this. I'll give you y equals 1 over x minus 3, and you'll tell me, oh, that got shifted left 3 spaces, or right 3 spaces in this case. If I say y equals 1 over x plus 2, you'll tell me that that's the parent function shifted up 2 spaces. And of course, we can put these two together just like with quadratics. So I might have something like y equals 1 over x minus 3 plus 2. And so you would tell me it's being moved right 3 spaces and up 2 spaces. Now, Desmos will not type in the equations of the asymptotes for you, but remember, by default, it's starting with the origin. So if I moved this rational function, in this case right 3 and up 2, then the asymptotes are going to change right 3 and up 2 as well. Okay. If you're asked to submit a sketch of the function, and you want to be kind of, at your best, so to say, you can change the lines to be dotted or dashed, depending on preference. You can do dotted or dashed. But that'll show you where your asymptotes are, and you get a little bit of better picture of what your hyperbola is supposed to look like. So for me, I would like you guys to do this on the assignments that are asking you to submit a screenshot. Because eventually, when we go back in person, right, we won't have access to Desmos all the time. We want to be able to do it by hand as well. So that's about half of your assignment, just being able to do one of those two things. If I give you the graph, I want you to be able to tell me the equation. And if I give you the equation, I want you to be able to tell me the graph. Okay? Because we are doing this online, right, most of the time I'm giving you the easier examples. I'm not trying to overcomplicate it. I just want you to be introduced to this topic, and I want you to be able to kind of give me the basics of, in this case, graphing rational functions. We can make this more complicated just like any other problem, but that's really what I'm having you focus on in this assignment. I do want to cover a couple other things here in this lesson. They're not going to be on your assignment or on your test. Again, online learning, so on and so forth, but I do want you to be aware of them. The other thing that can happen with a rational function like this is we can also have, in addition to asymptotes, sometimes we have holes. Now, our simple rational functions aren't going to have any holes in them. But what we can have happen, change this here, we can have not only asymptotes but holes as well. The only time we're going to get holes is when we have a more complicated rational function. Rational function, by definition, is the the quotient of two rational functions, if that makes sense, thinking back to how we classify numbers. So if I put one function on top of the other, then in theory, that is a rational function. Now, we're looking at cases where the degree of the denominator is higher than the degree of the numerator, meaning, looking at the degree here, x is a first degree, 1 is a constant, so the degree is higher. Now, in these cases, let's say I have x minus 3 over x squared minus 4x plus 3. Okay, this kind of looks very similar, or should look very similar, to, well, it's not going to do me any good if I don't get the right one. Give me just a second to tweak this here. Let's say I have something like what we were trying to do, x minus 3 over x squared minus 4x plus 3. Okay. Now, if I go back to my first example, y equals 1 over x minus 3, notice how it got shifted to the right, and the asymptote got shifted to the right. The asymptotes are always where I am getting a 0 in the denominator. So if I were to plug in 3 to this equation, 3 minus 3 is 0, and I can't divide by 0. That's why there is an asymptote that exists there. When we look at rational functions that have a degree higher than that, let's say this example, potentially we could have asymptotes or we could have holes. And so here, I end up with x minus 3 over x squared minus 4x plus 3. But at negative 3, if you look here on the graph, negative 3 is undefined if we trace it. By default, unfortunately, Desmos will not put holes in your graph. So if you wanted to put holes in your graph, you would have to type in the point, like where it should be, which is 3, 1, and then you can change it here. 3, 0.5. You can change it here to make that hole appear. And so then when you mouse over it, it'll tell you on the graph, undefined at that point. Okay. What makes the difference between an asymptote and having a hole in your graph is if the quadratic or higher degree polynomial is factorable. And we just finished Unit 3 talking about factoring. The denominator here, I could rewrite as x minus 3 times x minus 1. And when I do that, it's simplifiable, right? The x minus 3's would cancel out, and I'm left with y equals 1 over x minus 1. And that matches up to the graph that we already have here. Now, yes, we can simplify it, but it doesn't change the fact that in the original equation, there were 2 numbers that I could plug in to get a 0 in the denominator. We'll talk about this a little more when we get into our trig and our pre-calc towards the end of semester 2. But any number that I can simplify and kind of factor out, like the 3 here, x minus 3, that's when I end up with a hole. And if it's not able to be simplified, x minus 1, that's where I get my asymptotes. So the numbers that you can plug in that don't go away, those are your vertical asymptotes. Numbers that you plug in that potentially do go away, those are going to be holes in the graph. Like I said, I want you to be aware of this and introduce you to it, but for your assignment, it's just graphing the simpler examples where we have a slight change in the denominator, like y equals 1 over x minus 1, or where we are shifting it up and down, where I have a change on the outside. That's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon.